Hello everyone, welcome to the 8th session of quantum field theory. Today is finally the day that we are going to talk about quantization of the Dirac field, which leads into the concept of Pauli exclusion principle. At the end of this session, we are able to address the following question. What is the main difference between fermions and bosons? What is the connection of a statistics and a spin? And how to properly quantize the Dirac field. The Pauli exclusion principle is a very important principle that was stated first by Pauli at the first quarter of the 20th century. And the idea was that not any two fermions cannot occupy the same quantum state or the same quantum number. So basically, if I want to visualize it, again, if there are some state, they are not necessarily the energy state, but they can have all sorts of quantum numbers as the label. You can call it epsilon 1, epsilon 2, epsilon 3. For example, for the case of hydrogen atom, that is N, L, and Ns of those particles. If you remember from the chemistry of high school, there are basically ways to label electrons inside of the hydrogen atom, and they're basically states or quantum state or quantum numbers. If there is an electron, for example, here, already occupying that particular state, the other electron cannot go down. And you might ask why? Why is it really like that? What makes this electron kind of reject the other electron? Is there any force? Is there any kind of repulsion between them? And the answer is simpler. The answer is in the algebra. And we're going to show that fermions are different numbers. They're Grassmann variables. And the bosons are basically regular numbers. And Grassmann variables have some weird anti-commutation relationship. So the reason that is happening is because anti-commutation. So we already showed that in the case of Klein-Gordon field, we have commutation, which means that if we have two operators, A and B, we define the algebra between this A and B. So let me just use, instead of A and B, I'm going to use the regular commutation that we use. For example, we have A of P and then 8 dagger of P prime, and that is equal to delta of P minus P prime times 2 pi the power of 3 for normalization. But the point is, we define a commutation, which means we calculate this variable, AP, A dagger P prime minus A dagger P prime AP. And we are going to show that this is not going to work out for the Dirac particle. This is not going to work for the Dirac particle because it doesn't set any bound for lower energy of the system. So for the first time, Paul Dirac noticed that the disaster happens when we have this kind of commutation algebra. And this commutation algebra is basically creating some negative energy. We're going to talk about it, don't worry. But we need to have some recap from Klein-Gordon field to clarify some points before getting into the concept of quantization of the Dirac field. So if you remember, we talked about Klein-Gordon field, and honestly, we really didn't talk about the complex version of Klein-Gordon field. I did not quantize it, but I think in the second video, I talked about the symmetries, Noether's current in the complex version of the Klein-Gordon. But now it's a good time to really talk about the quantization of complex Klein-Gordon field. So Klein-Gordon field has two versions. There is a version which is a real number, real valued field, and there is a complex version. And both of them respect U1 symmetry. But U1 symmetry in a concept of complex number is going to give rise to some form of electrical charge. And we said the electrical charge in those quantized version is going to be like this. The Q, or the charge, is going to be sum over all momentum. And we're going to have something like this. A dagger of P and A P times the charge, or we don't have E here, we don't have any specific E, but here the unit of charge is 1 basically for the case of Klein-Gordon field, but we have something like this, B dagger of P and B of P. And we really didn't say what are these B. This can be seen as positive charges and this can be seen as negative charges, and there is a minus sign between them, and this minus sign is somehow indicating that these two charges are the opposite direction of each other. But again, what is A and what is B? Because as far as I remember, in the Klein-Gordon field, we only have A, or creation and annihilation operators. So if you remember, phi of x was equal to, so I'm just writing down again the quantization formula. Nothing really complicated. And remember, this term was for making it Lorentz invariant. And now we have A dagger of P exponential of minus IP dot x plus A of P exponential of IP dot x. And what does it mean? So there's two terms here. One of them creates, it is the red one, and one of them annihilate. But the same type of particle. So we only have, let me choose another color. So we only have 1 degree of freedom. What does it mean? It means that in my Lagrangian I only have phi. So I have 1 degree of freedom. So therefore, I have one type of creation and annihilation operator for the same type of particle. And when I say same type of particle, which means that these two particles are not distinct from each other. They are not orthogonal. They are not different entities. They are the same thing because in the real value Klein-Gordon field, that particle is anti-particle of itself. So no surprise. So one of them creates and one of them destroys. But there is a very interesting analogy on that. So we said these fields are basically moving the free particle. So it creates, annihilates, everywhere in the space-time. It creates, annihilates, and they move around those particles. So imagine that I'm focusing on the first term here. Let's say I'm focusing on this term. So this one creates on the direction, to the left direction probably of time. So my field is creating a particle then to the left. So it's just constantly creating particle to the left. So we said the real value Klein-Gordon field, those particles are not charged. They're neutral particle. But for now, just imagine that instead of being neutral, they're charged. So there's something like electron. Again, you might say electron is a fermion, blah, blah, blah. But now just focus on the analogy. So we have the electron and we are creating the electron to the left. Right? It's going to the left. And imagine this right and left are direction of time, right? Direction of time. So the negative current is flowing to the left. So negative current to left. Now I'm going to this annihilation term. So the creation term was A and annihilation term was B. And now to make an equivalent situation of negative current moving to the left, I can say instead of moving electron to the left, I'm removing electron to the right. So imagine, so I'm not creating anti-electron. This is a very important case here because, again, there is no antiparticle. So imagine electron is basically the antiparticle of itself. So to create a current to the left, I should destroy electrons to the right. So now instead of creating these blue circles, I'm creating these empty circles. So these are hole, kind of hole. You destroy an electron. So when you make hole here, to what direction? To the right. So when you make a hole, you are destroying the negative charge to the right. So you can say this is an equivalent version of flowing charge to the left. But instead of flowing the charge into the left, creating the charge into the left, you're destroying the charge to the right. So that's how you have only one degree of freedom and you have only one type of operators. This A of P, they create the Klein-Gordon particle. Now you change your field to a more advanced field, and you said that's a complex Klein-Gordon field. So phi of x is not the only degrees of freedom. You have also phi of x star. And when you have a complex number, as we said, you have 2 degrees of freedom because you have I plus AB. And you need to know this A and B kind of independent to know the number. Or one way is to have the conjugate version of the number. So you have I plus IB and you have I minus IB, and you call it phi, and you call it phi star. So if you have, again, phi and phi star, you know A and B, but you need to have 2 numbers. So now this is a more complicated field, and the procedure to quantize this field is like this. So I have D3P, everything is the same. Energy factor is the same. And then I have A dagger of P exponential of minus IP dot X. So that part is the same. The other term is B of, let's say, B of P, but it shouldn't be a dagger. It should be a B. Or you can actually interchange these two. Let me just say, for example, I have A dagger of P plus B of P, an exponential of IP dot X. And now you have 2 operators, B operators and A dagger. So A dagger creates a phi, basically particle, and B annihilates a phi star particle, and they are different. A way to look at it is like this. So you have creation of electron. Imagine this is your time. Maybe I should show the time like this. So this is time equal to 0. And maybe that's how I can kind of show how the time is mirrored. So probably this direction is negative direction of time. This is a positive direction of time, but there is no basically the difference. So while you are creating electron in the positive direction of time, it is equivalent to destruction of the electron into the opposite direction. So maybe I shouldn't put these two under the same axis here, because now we might think, oh, the time is the same. But there is like a kind of mirror time equal to 0. So there is like the positive time and the negative time. So for the case of ordinary Klein-Gordon, creating electron in this direction is like creating holes on the opposite direction. So these are like filled circles, and these are like empty circles. So yeah, this is better. But anyway, I hope that the concept is clear right now. So when we have an antiparticle, then we do not need to create holes. We can create those antiparticles, and they have an opposite charge, and the total charge of the system is the difference between the number of let's say phi particles and the number of phi star particles, and when you subtract them, you have the net charge of the system. But we don't really have electromagnetism here. It's just Klein-Gordon, and there's no electromagnetism. So when you think about electrical charge, think about electrical charge just as +1, -1. There is no charge of the electron or something. Anyway, so there is a new video in my channel. I'm talking about measuring the charge of the electron if you're interested in. And it's interesting that how we formulate the mathematics of it somehow came after many of the discovery that was made in the 20th century. Okay, so now we know about how to quantize a complex Klein-Gordon and how to introduce this B. And I have to point out that this B and A do not see each other. They don't have any algebra between them. So that's why they're orthogonal. Positron and electron are different entity. Positron, again, positron and electron are not for Klein-Gordon field actually. Klein-Gordon, it's actually Dirac particles. So both of them, we're gonna see how positron and electron are Dirac particle fermions. But just for the case of some hypothetical spinless particle, which is charged, you can think about them as two orthogonal states. So I can only define a commutation relationship between A of P and A dagger of P prime, delta of P minus P prime. There's a 2π3, but I'm leaving it out. And then there is a BP, and then B dagger P prime, delta of P minus P prime, okay? But any relationship between A and B are 0. So fortunately, they don't see each other. A dagger of P, B of P prime. So these are 0. So there is no kind of uncertainty between creating and annihilating a particle and its antiparticle. So it can be done simultaneously. All you need to care is to see how one particle is creation and annihilation follows some uncertainty. But anyway, this is the algebra. This is the commutation algebra for Klein-Gordon. And again, it's a commutation algebra. It's a commutation. And we're going to see commutation is not going to work for Dirac field. So let's go to Dirac field. So we have the Lagrangian of Dirac, and we have psi bar. And we already talked about what's the philosophy of bar and, those gamma 0. And then I have in between the Dirac operator. So let's say gamma mu, d mu minus m. And then I have psi of x. Okay, that's the Dirac Lagrangian. And we can talk about the Dirac Hamiltonian. You can calculate Dirac Hamiltonian from Dirac Lagrangian. I'm going to skip the calculation, just going to write down the form of Hamiltonian. The form of Hamiltonian is psi bar psi. And then in between, I have something like minus alpha dot a gradient plus m. And alpha, alpha is basically kind of vector, so there is an inner product between them. So alpha is gamma 0 gamma. So by vector, I mean only the spatial component. But again, gamma matrices are not vectors. They're not vectors, but you can think about them like vectors because there is one index here. So there is, one index up here. So you can define alpha like this, and you can do it as an exercise, how to calculate the Hamiltonian, the formula, the how to get Hamiltonian out of the Lagrangian by taking derivative with respect to conjugate momenta. But anyway, the Hamiltonian is similar to Lagrangian, and there is a plus sign here to kind of standing for adding the kinetic energy and potential energy. So you can think about this part as kind of kinetic energy. It's not kinetic energy exactly, but this is also the mass term or self-interaction term. So that's a Hamiltonian. And now the next step is to quantize the field, which means that I write down psi as a function of creation and annihilation operator and look at the Hamiltonian. That's what we did last time. Again, a recap to Klein-Gordon field. So in Klein-Gordon field, we quantize the field and then we put the field in the Hamiltonian. And, we had to do a little bit of algebra to get rid of the terms and cross terms. And at the end, we get up something like that. 2π3, 2EP. No, sorry. there is no 2p. But you know, the essential terms inside of it is going to be a dagger of p, AP, EP plus b dagger p, b, p, EP. And you know, we're talking about, again, a complex now. Anytime probably I'm going to talk about Klein-Gordon is a complex, because complex version is the good one, is the it is more complete. And this is kind of number operator. So we're basically counting the number of particles and antiparticles and then multiply them by their characteristic relativistic dispersion. The relativistic energy. And the relativistic energy obeys a dispersion relationship. Right? EP2 is equal to P squared plus M squared. And there is something about it. Again, I want to remind you in the case that you might make a mistake between that. Now, if you want to solve EP has a plus or minus P squared plus M squared. And some of you might wonder whether E can be negative. What about this negative sign? And we discussed it in the first or second video that we would keep EP or energy as a positive defined variable, but we define this two direction of time. That's a trick. So when I'm talking about EP plus or minus, I'm talking about positive frequency answer and negative frequency. And you know, maybe frequency is a better word because frequency is this, EP times T. And that's basically the frequency of the evolution of the particle. Actually, the frequency is this coefficient here. But when you have two types of answer, you have exponential terms like this. Exponential of minus I EPT and exponential of plus I EPT. And again, we said to preserve the energy as a positive, well-defined direction, we kind of absorb this minus and plus sign into the time. So we get this sign out of the relativistic energy and, you know, put it into the time direction. And that's the beauty of it. But energy is positive. And this is the energy of one single mode, energy of one single particle. Now, when you say the Hamiltonian of the system is the integral over now number of, let's say, NP, number of positively charged particle times the relativistic energy, plus number n prime of P, the number of negative charges with the relativistic energy of P, and that would be the total energy of the system, or energy of the field, energy of the configuration. So energy of the configuration is the sum of energy of each mode times the number of that mode, and that would be the total energy. So we need to make a distinguishment between energy, relativistic energy, positive and negative frequency answers, and the Hamiltonian. So I hope that it is clear by now that how these variables are all energy, but they are not the same energy, right? The word energy might be a little bit misleading. Now, let's go back to the Dirac field again. So we got this recap from Klein-Gordon field and go to Dirac field. So I'm going to write down again the Hamiltonian. The Hamiltonian of the Dirac field is psi bar minus I alpha plus m psi. And now it's a time that I throw out the whole concept of the quantization. So psi of x is going to be similar to Klein-Gordon. And then inside of it is a little bit more complicated because it's a spinor. So now we have before I put this bracket, now I have a spin. So sum over a spin. And this spin is 1 or 2 because we're talking about half a spin representation of the spinor, right? We're talking about spin up, spin down. Of course, we can have more complicated fermions that their spin is 3 over 2. But right now, we're leaving them out. And then I have A of P exponential of minus I P dot X, but there is a U of P here. That's a spinner for the answer to the Dirac equation, and I have the index S on top of that. And then I have the other term, B of P dagger S. The exponential term is P dot X. And then I have V of P and the index of S. So now I think the new thing about it is this index S, and also the fact that these V and U are there. So of course, psi bar of X is going to be D3P now I have the same sum over a spin. Now A of P is going to be a dagger, exponential is going to be P dot X, and U is going to be U bar, and then S, and then P, and then B is going to be P, S, exponential of I, P dot X, V bar, P, S. Okay, now I have these two types of field, 2 degrees of freedom, and then this is how I quantize them. So this is basically the same procedure as Klein-Gordon. You create, but you have these, answers. You need to have those. Now, if we want to calculate the Hamiltonian, we need to know something. We need to remind something again. We need to know this completeness relationship. So if we are summing over a spin of U of S of P times U bar S of P, that would be gamma P plus M. And if I have V of SP, V bar of SP, that's going to be gamma P minus M. So now Hamiltonian is going to be the integral over dP, d3p prime, 2 pi 6, and then I have 4 EP prime, and then I have sum over S and S prime. You see it's getting more complicated. But I have A of P, S, A dagger of P prime, S prime. And then I have U dagger of P. And then I have gamma 0. And then I have other terms like minus gamma I, the ith derivative plus M times U of P prime S prime times exponential of minus I P minus P prime X plus B dagger of S P B of P prime S prime V bar of P and S gamma 0 minus gamma I derivative I plus M V prime of P prime of S prime, and now exponential term of I P minus P prime of X plus cross terms. So we are just picking up diagonal terms. So there are some cross terms, and these cross terms are going to be 0 because there is a creation and annihilation operator. So some of them are just make the vacuum. If there is any state acting on them, that would be 0. So good thing is that we are going to get rid of this cross term because they're going to be 0, and then we are only have to deal with this term here. This complicated term out of the product of the two fields, right? And those cross terms, they are going to be like this. So we have terms like U dagger of P and S gamma 0, and then you have V of P prime and S prime. and that's equal to 0. So good for us, really. U and V don't interact with each other that much. So we only have to deal with U bar and V bar. So same for V bar dagger of P prime, S prime, gamma 0, U of P and S is also equal to 0. So those cross terms are like this. We get rid of them, and then we can simplify the Hamiltonian to this form. The Hamiltonian is going to be like this. The Hamiltonian is the sum over dp, sum over a spin, E of P, A dagger of SP, A of PS, minus EP of BP, S, and B dagger S of P. Okay? As you can see, this energy doesn't have any spin dependence, so this S is only up here. So that means the spin doesn't contribute into the energy of relativistic particles. So this is not something very new. But now let's go to the second term. So the first term here actually is the counting operator. So we basically have the number of, let's say, positively or negatively charged particles. So the number of first particle minus the energy of the second one. But the second one is not a dagger A. It's not like a dagger and the operator. It's the opposite way. So it has it's a operator and the dagger of the operator in front of it. And now this is where we can show that how commutation and anti-commutation are different. How one of them is basically creating negative energy, infinitely negative energy for the Hamiltonian, and one of them doesn't. And it's basically all because this minus sign is coming from the Dirac equation. In the Klein-Gordon equation, that minus sign becomes plus. So we don't have that problem in the Klein-Gordon. And that's why in Klein-Gordon we can use commutation relationship. But there is a minus sign here, and we're going to see how this minus sign is going to make this disaster. So now I'm going to write down B, P, S, B dagger S of P. I'm going to use the algebra. So imagine that I say the commutation between BS and B dagger of SP is equal to identity. Why? Because those delta functions are not non-zero. In the case of P equal to P prime, S is equal to S prime, then we have non-zero delta function. And forget about how delta function becomes infinite, but let's just think about it as the identical operator. So what I have is that BSP. So now I can just write it down as BSP, B dagger of PS is equal to I plus B dagger of SP, B of SP, right? And this plus here is coming from the commutation because on the other side is minus. Now if I just put this inside of this equation, I'm going to get a Hamiltonian like this. Spin. Now I have EP, A dagger, A, P, P, S, minus EP, B dagger, S, P, B, S, P, minus I operator. So that's the vacuum energy. We don't care about vacuum energy. So let's just forget about that vacuum energy. EP, there is also EP here. But we don't care about this identical part. This is the vacuum energy. But look at this energy. So if you're creating more of this B type of particle, you are lowering down the energy of this state. And you're making the total Hamiltonian negative. And what does really stop the system not to collapse into the lowest and lowest energy? So that's a paradox. You know, even though we said the energy is positively well defined, negative and positive frequency answer, they both contribute into the Dirac field. But the final Hamiltonian is the energy of particles minus the energy of antiparticles. And it looks like that the antiparticle have negative energy. That doesn't make sense. Physically, we don't have negative energy. So Dirac tried to justify why the system doesn't really go down into the infinitely negative energy state. And he said the reason the electron is not just falling down into those lower and lower energy state is because those states are already filled, and there is a lot of electron down there that from day one that this thing was created, these electrons are there, so it would not let the electron go down more because those states are already occupied. Well, he was technically using the Pauli exclusion principle. So this sea of electron is somehow preventing this electron to go down. But then he kind of fixed the problem by anti-commutation. And he predicted that, okay, if I'm using this anti-commutation, there should be antiparticles. And he called those antiparticles protons. And, he didn't know about the positron. But the mistake that he made was that proton mass is 2,000 times larger than the mass of the electron. So proton cannot be the antiparticle of electron because, as we said, there is no difference between the mass of particles and antiparticles. So there should be another way. The easy way is to just use anti-commutation instead of commutation. So I'm going to have, instead of B of PS and B dagger of S and P, instead of commutation, I'm going to use anti-commutation. So anti-commutation means I'm going to have BSP, B dagger SP plus B dagger SP, B SP is equal to identity. And now I can say BSP, B dagger SP is equal to identity minus B dagger SP, BSP. And that's how you just simply solve the problem. Now if you put up this with that minus, with the minus sign, we're going to have, so the Hamiltonian is going to be the sum over momentum, sum over spin. Now I have A dagger A, P, P, S, S times EP plus B dagger B, S, S, P, EP minus that vacuum energy sign. Who cares about vacuum energy? But what we care about is this term, which is now positive and positive. So you can create particles and antiparticles, and it doesn't generate infinite amount of negative energy. And that's how you just replace commutation with anti-commutation. Very simple algebra, but there is a huge consequence out of that. And we're going to see this anti-commutation really makes this number weird. Probably we're going to talk about Grassmann variables in the next session, but there is a deep consequence of that. Imagine that you want to create a particle, but 2 times. So in the Klein-Gordon field, let's go back again to the Klein-Gordon case. In the Klein-Gordon case, I could say A dagger of P and A dagger of P prime. No, sorry, A dagger of P. So I'm trying to create one particle out of the vacuum, but 2 times. So I want to create 2 particles. So you see, this is going to be P and P. So I would have 2 particles in the same state. No problem. Now imagine that I'm dealing with the fields that they anti-commute. So A dagger of P anti-commute with A dagger of P. So why is it not a problem? Why is it not a problem? Because if I say A dagger of P anti-commute with A dagger of P, so anything anti-commute with itself, so that would just tell me A dagger of P is equal to A dagger of P, A dagger of P. So it's a trivial thing, you know, a dagger of t. So we can create two particles and no problem. They can interchange the order of creation. Now, let me just do anti-commutation. You're going to see that that's going to make a huge difference. So I have a dagger p. So as we said, the anti-commutation is only stands for a and a dagger. So 2 a dagger are 0. They're anti-commutation. So I'm going to have a dagger p plus a dagger p is equal to 0. So 2 a dagger p is going to be 0. So a dagger p is 0. So when I try to create the same type of particle with the same quantum number, imagine I also put this s index on top of them, that would be null. So if we try to create 2 electrons in the same state, that would be null, that would be 0. And that's basically the Pauli exclusion principle. So, you know, that's why you cannot put 2 fermions in the same state. And that would make fermions very useful. Very, very useful. You know, the first thing that is useful is that imagine in a hydrogen atom, there is a proton here. And, you know, there are electrons in different orbits. And, you know, imagine the first electron is going to stand in a ground state. And the second electron is going to stand in n. So this is, imagine, n1, n2, so these integers. So basically, the fact that fermions cannot all go down to the same ground state makes our world stable. Because we have fermions. Fermions are not So the fermions are not condensating in the same state. They do not condensate. They do not all go in the same state. There is a hierarchy, and that hierarchy creates a lot of stability. And that's why our world is made of matter, and the matter is fermion. So matter is really stable because it's fermion. And we're going to see in the path integral, these numbers, the Grassmann numbers, so these numbers are ordinary numbers. These are the numbers that they commute. But these numbers that anti-commute, they are called Grassmann variables. So Grassmann variables are really interesting because imagine theta is a Grassmann number. Theta square is going to be equal to 0. So you're dealing with numbers that when you multiply them 2 times to themselves, they're going to be 0. So they're going to be 0. So these numbers are really small. The range of those numbers are really small. They cannot get so big. And any function of those numbers can be expressed in terms of a linear expansion because the other terms are 0. So c theta 2, imagine d theta 3. Imagine if you can analytically expand any function, Taylor expansion, these terms are going to be 0 because the Grassmann numbers are small. So any function of them can be expressed as the linear combination of some number plus b theta. So it's a Grassmann number. But we're going to see this particular useful way that we can expand any function into a linear function makes our life easy when we want to calculate integrals because those linear functions, they have a very, very well-defined integral. So if you technically try to get the integral of f of theta over d theta, you don't really have any complicated function to integrate over. You're dealing basically with a plus b theta d theta. So you're going to be a theta plus b theta squared divided by 2. And then again, theta squared is going to be 0. So these Grassmann variables are amazing. And they make our life very easy. They make path integral easy. And they also make our universe very stable. And Pauli exclusion principle is one of those principles that I was always surprised how it was discovered. It is the connection between a spin and a statistic. So a spin, a statistic. How? The spin is represented by a spinner. And the spinner is represented by Dirac equation. And Dirac equation is going to give us Dirac Hamiltonian. And Dirac Hamiltonian is going to force us to accept this anti-commutation relationship because we want the Dirac Hamiltonian to be positive. So when we accept that, we define this as statistical limitation, that we cannot put two fermions in the same state. So from here, so I started from a spin, spin half particles, and I get into the anti-commutation, and from anti-commutation I go to a statistic. And that's why fermions obey Fermi-Dirac statistics, and bosons obey Bose-Einstein statistic. So bosons, let's say bosons, it can be basically you can have a spinless bosons, or you can have bosons with a spin. In the standard model, we are dealing with this kind of the bosons that they actually have a spin, and they're called gauge field. And these gauge fields are photons, gluons, W and Z bosons. So this is the electromagnetic force carrier, this is the strong force carrier, and this is the weak force carrier. But the point is, those bosons, they obey Bose-Einstein because they don't have anti-commutation. They have the commutation relationship. And that's why they can condensate. If you hear about the word Bose-Einstein condensation, is that imagine that you have a liquid very near to the temperature around 0. So basically, not 0. You can never get to the 0 temperature, but near 0. It's really small. So when you have a very small temperature, your particles start to go down more and more. At some point, all of your particles are going to end up in the same ground state, and they would condensate. And people got Nobel Prize for that. It was first predicted by Einstein, but in the 90s, people saw it for the first time experimentally, because we didn't have the technology to really cool down some bosonic matter up to the point that everything really goes down into the ground state. So the bosons have condensation, fermion don't have. So that's why we have a very stable fermionic world. Okay, so for now, I think we covered what we wanted to cover. Now, first we introduce the concept of Pauli principle. We talked about complex Klein-Gordon field, how 2 degrees of freedom can lead into different interpretation of the current. So if you don't have antiparticles, there are 2 currents. One of them is holes and the other one is creation. If you have an antiparticle, you can create particle to the left, and on the opposite time direction, you can annihilate the antiparticle of the of that particular field. And then you define this commutation algebra. And then we went to Dirac equation. We wrote down Hamiltonian, tried to simplify Hamiltonian. But at the end, when we got the Hamiltonian right, we realized that the commutation destroys the logic of it, because we're going to have infinite amount of negative energy. So instead of commutating, we started to anti-commute them. And let me again write down this anti-commutation relationship. It's very similar again to the commutation. So A dagger P, A of P prime S is going to be delta S prime, delta P minus P prime, 2 pi 3. I mean, it doesn't matter. You can also interchange them. It's a conventional term, but only A dagger and A together. So B dagger P, B of S prime, P prime, similar. And A and B do not see each other. So A dagger, B, P, P prime, S, S prime. They don't see each other. Similar for A and B dagger. So they don't see each other. So that's good. So this is a new life. The new life is that we have 2 types of particles, fermions and bosons, and they have a very different behavior. So fermions, we can deal with them better. It's easier. especially in something like lattice QCD. If you go more into the detail of something like lattice QCD, you see in lattice QCD, you can kind of get rid of the fermionic degrees of freedom and only deal with the gauge field on top of that. But yeah, it's a long way up to that point. But, you know, I'm happy that I finally covered this area. In the next session, we're going to talk about the remaining concept in the Dirac field. So sorry that it took longer for me to kind of finish this Dirac field. It's a complicated area and there's a lot of details. And you can still go into the textbook like Peskin and follow up many of those calculations. But the core of the topic was that fermions, anti-commutation, bosons, commutation. So thank you so much for watching Quantum Field Theory 8. We're going to be soon with you with Quantum Field Theory 9. Thank you so much. Goodbye.